Okay, so I wanted to give a second lecture on liquids and gases. Remember, I'm covering both chapter 13 and 14, but you're going to hand them in one in next Monday and one then the Monday after that. So again, last time we said right here that when you're floating right here, now we're floating right there, your buoyancy force equals your weight because of Newton's second law right there. And we said the buoyancy force is equal to the weight of the displaced if it's liquid or air or whatever, but we're in liquid right here. And so we said objects displace their own weight right here. So the weight of this object is equal to the weight of just the water displaced. Remember, the water displaced is just the part that's right there. Well, suppose that this could have been a boat right here. Suppose this boat, you throw something overboard right here, maybe a piece of wood right here. If you throw a piece of wood overboard, then the wood is just going to stay floating right here. And so the total buoyancy force is still equal to the total weight right here. And so since the buoyancy force doesn't change because the weight didn't change, the weight of the displaced liquid doesn't change, so this level, this water level right there at the side of the pool or wherever, doesn't change right here. As long as everything stays floating, this water level stays the same. So let's say you threw over ice. If you threw over ice right there, ice doesn't sink in the water, so as long as it stays floating, this level stays the same. Or this could have just been a big chunk of ice. If this would have been a big chunk of ice, when the ice melts, this level doesn't change right here. As long as everything stays floating, and when ice melts, it goes to water, and water doesn't sink, it just stays floating right there. So as long as everything stays floating, the water level here doesn't change right there. Well, let's say now that we're sunk. We have an object that's sunk at the bottom of the pool, say. Now we've got an extra force here. We've got the floor force pushing up. So now we've got the buoyancy force and the floor force pushing up. We got the weight going down, and we know we're in equilibrium again. So we know the buoyancy force plus the floor force up has got to match the weight going down. Well, since the floor force is helping hold it up, the buoyancy force must be less than the weight right here. And we say objects displace their own volume. Whatever the volume of this is the volume of the water that was displaced right there. So you notice when we're floating, our buoyancy force equaled our weight. When we're sunk, our buoyancy force is less than our weight. So if you ever go from a floating position to a sunk position, it looks like the buoyancy force drops right there. If the buoyancy force drops, that means the weight of the displaced liquid drops, which means this water level goes down right here. So anytime you go from a floating position to a sunk position, the water level will always drop right here. And here I can show it right here. Here I have a piece of wood floating in water, and tight underneath it I have a small heavy lead weight right there. And the water level is right there at that point. Now I come along and I cut this string right here. That lead weight goes to the bottom, doesn't take up any more space. He was already taking up all this space. The wood now bobs up a little bit, and now all that space underneath the wood is now going to be filled in with water, so the water level drops right there. If you have a boat in a lake and you put a hole in the boat and the boat sinks, the water level at the side of the lake will go down. Anytime you go from a floating, you're already floating, to sunk, then the water level drops. Now if you put things in the water from outside, then it'll go up, but we're already in the water right here. So what about if you had a big piece of ice in here that had some metal pieces in there? Well, as the ice melts, the water will stay floating, but the ice pieces, the steel pieces or whatever I have will drop. The water level will also fall right here. So anytime, just remember that, anytime you go from a floating to a sunk position, the water level drops right there. Okay, one last principle I wanted to go over between liquids and gases, and something called Bernoulli's principle. Bernoulli's principle says if you start moving gas or liquid, it doesn't matter, that lowers the pressure right here. Now, when we say moving, we mean like a wind. So here, if I have wind or water flowing all together, that's what we mean moving. If I have a container filled with a gas and I heat it up and the gas atoms start going faster, well, there the pressure increases. So I'm not talking about this situation. I'm talking about just movement, bulk movement of the material. Whenever that happens, the pressure drops. And this comes up in a lot of places. One is the frisbee. Here I have a frisbee right there. When you throw a frisbee, air goes over the top quite fast. It can't go fast inside because of the curl on the plastic, on the rim of it right there. So the pressure is lower here and not lower here. Well, if the pressure is lower there, that gives you an upward force right there, upward force. And that's what lifts the frisbee up. And you spin it to stabilize it. If you didn't spin it, it wouldn't be very stable. If we look at an airplane wing, this is just the wing going this way. They form the wing such that when air flows over the top, in the bottom, it goes, this is a longer path, so it goes faster over the top. When air goes faster over the top, lowers the pressure there as opposed to there, gives you a lift. Pressure times area is the lift. That's why with a big commercial airliner, you need big area wings, because it's the pressure difference times the area right there. If we look at an umbrella over here, umbrella, usually whenever you bring it out, it's windy. Wind goes over the top, can't go fast here, it gets kind of trapped here, which means you lower the pressure there. It wants to bring the umbrella up right here. So it kind of tries to lift you up right there. If we look at ocean waves, here's ocean waves. Let's say during a hurricane where you got really big winds coming through here. You got fast moving air on the crests. Down here, air gets kind of trapped. It's not going fast. So this lowers the pressure, pulls the water up right here, which makes the swells even larger right here. That's why you have huge swells during a hurricane. If Bernoulli's principle were reversed, we would have flat, calm water during a hurricane. It just doesn't sound right. Or we could look at baseball right here. When pitchers are throwing curveballs right here, what do? They put a spin on the ball right here. Well, if the ball's going this way, air is going by it. But if they put a spin on the ball here, it kind of kicks the air underneath and slows the air down on the top. Well, if the air is going faster here than there, then this is a lower pressure, and the ball would want to drop a little bit faster than it would if you didn't put a spin on it. If you put the spin the other way, it would stay up a little bit more. If you put a spin sideways, you could go off to the left or off to the right. So you can affect the ball a little bit right here. And if you really want to kick the ball well, then pitchers, they're always trying to scuff up the ball, because the more it's scuffed up, the more they can kick the air. And the umpire's always throwing new balls in, so the real battle is between the pitcher and the umpire, not the pitcher and the batter right here. Now, you notice the best stadiums to pitch would be stadiums that the air is real heavy, like down in the south right here. The worst place to pitch would probably be in Denver, because the air is quite thin and gravity is a little bit weaker, so the ball goes a little bit further right there. So if you're a pitcher, you might not want to pitch in Denver right here. Okay, so you notice this all over the place. When you turn on a shower and you got a curtain, sometimes the curtain will move inward because the air is moving fast, because you just brought all that fast moving water in there. If you get two cars moving by each other on a desert road, when you first pass each other by, you feel a little bit of a jerk towards them. Again, you're lowering the pressure between the two right here. So this comes up all over the place. It's just called Bernoulli's principle right here. It's just faster moving, and works for both gas or water right here. So, okay. So that'll cover everything you need for the liquids and the gases.